You know how some chemical reactions are just boom, an explosion, over in a flash, and then others can take centuries to happen? Well, that's the whole field of chemical kinetics, studying how fast these things go. But what if I told you that a single reaction could look like it's going at multiple speeds all at the same time? It sounds a little weird, right? Well, let's get into it.
So if someone asks you, how fast is a chemical reaction, you'd probably expect a pretty straightforward answer, a single number, like a speed limit. But as we're about to see, if you actually go and measure different parts of the very same reaction, you can get completely different answers. So which one is the real speed?
To really wrap our heads around this, we're going to look at a classic example, the decomposition of ammonia. This one reaction is going to show us the problem perfectly. And also, the really elegant way chemists figured out how to solve it. Okay, so here's our reaction. We've got 2 molecules of ammonia breaking down into 1 molecule of nitrogen and 3 molecules of hydrogen. Now, the most important things for us to focus on right now are those numbers out front, the 2, the 1, which is kind of invisible, but it's there, and the 3. These are called stoichiometric coefficients. Fancy word, I know, but all it really means is it's the recipe. It's the ratio of how these chemicals interact. And trust me, they are the absolute key to this whole puzzle.
Let's put some actual numbers on this to make it real. Let's say we're in the lab and we're measuring the rate that nitrogen gas, N2, is being made. And we find that it's appearing at a rate of 0.1 molar per second. Okay, so the big question becomes, if we know that speed, what are the speeds for the other 2 chemicals in the mix?
To figure that out, we go right back to those coefficients, that 2 to 1 to 3 ratio. That ratio is going to tell us everything we need to know. It basically dictates the relative speeds of everything involved. So let's just follow the math and see where it leads us.
First, though, there's a quick but super important rule of the road. Think about it. Products, like our nitrogen and hydrogen, are being created, right? So their concentration is going up. That means we give them a positive rate. But the reactants, like our ammonia, they're being used up. Their concentration is going down, so they get a negative rate. Just remember that. Positive for products, negative for reactants.
So, what about the hydrogen? Well, our reactions recipe tells us that for every 1 molecule of nitrogen we make, we create 3 molecules of hydrogen. That means it's got to be produced 3 times as fast. So if nitrogen appears at 0.1 molar per second, hydrogen is just zooming along at positive 0.3 molar per second. And now for our reactant, the ammonia, NH3. Again, look at the recipe. For every 1 molecule of nitrogen we produce, we had to use up 2 molecules of ammonia. So its rate is twice as big as nitrogen's. And because it's a reactant that's getting used up, its rate of change is negative. That puts us at negative 0.2 molar per second. Okay, let's just pause and recap what we've got. We have a rate of positive 0.1 for nitrogen, positive 0.3 for hydrogen, and negative 0.2 for ammonia. And this brings us right back to our big puzzle. We've got one reaction, but we're sitting here with 3 totally different numbers describing its speed. I mean, how can that be?
Well, the short answer is, it can't. Chemists obviously needed a way to talk about the speed of a reaction with just one single, unambiguous number. And that's exactly where the concept of the official rate of reaction comes into play, to bring a little bit of unity to all this apparent chaos.
So, the solution is to define this official rate of reaction as a single, always positive value for the entire process. By convention, chemists standardize this rate. A really common way they do this is to just say the overall reaction rate is equal to the rate of the substance that has a coefficient of 1. And in our case, hey, that's nitrogen, which we said was appearing at 0.1 molar per second. But how do we prove that all those different rates actually point to the same overall speed? For that, we use a simple but really powerful tool called a rate expression. Think of it like a master formula that converts any individual rate into the one true rate of reaction. And making one is actually super easy. You just start with the individual rate of change we already found. Then, for any reactant, you flip the sign to make it positive. And the very last step for any substance is you just divide by its stoichiometric coefficient from the recipe. Let's actually see it in action. Okay, this right here, this is the big aha moment. Look at this. For nitrogen, we take its rate of 0.1, we divide by its coefficient of 1, and we get 0.1. Okay, no surprise. Now for hydrogen, we take its faster rate, 0.3, and divide by its coefficient of 3, and what do we get? 0.1 again. And for ammonia, we take its rate, negative 0.2, we make it positive, and then divide by its coefficient of 2, And once again, we get 0.1 molar per second. No matter which chemical we measure, the rate expression gives us the exact same unified rate of reaction.
We're almost there, but there's just one final, common trap we need to talk about. It all comes down to the precise language we use when talking about reactants and the difference between the word change and the word consumption. The source material for this had a fantastic analogy. If you went to a casino and someone asked, "How much did you lose?" you wouldn't say, "I lost negative $50, right? That would be confusing. You'd just say $50 because the word lose already implies the negative direction. It's exactly the same in chemistry.
So let's be super precise. If a question asks for the rate of change of ammonia, you absolutely have to include that negative sign to show its concentration is decreasing. So that's negative 0.2 molar per second. But if it asks for the rate of consumption, the word consumption is just like the word lose. The direction is already implied. So for that, the answer is just the positive value, 0.2 molar per second.
So we took what looked like 3 different speeds and we unified them into one single rate with a simple but really powerful idea. So the final question is, does this work for really complex reactions? Like the ones happening in a living cell? The amazing answer is yes. This core principle of using these ratios to find a single true rate is the foundation that lets chemists make sense of even the most complicated systems in the universe.